Hello guys, welcome back to MJ School of Mining and Geology. In today's lesson, we are dealing with eutectic and peritectic in phase diagrams. Don't forget to like, share, comment, and hit the notification bell below so that you get notified once we upload new content. So if you haven't yet visited our videos, our video on the phase diagrams or introduction to phase diagrams, wherein we're talking about the binary system, especially albite and the anorthite phase diagram, you are more than welcome to visit that. All right, but let's first understand what is a eutectic point. All right, eutectic point represent a fixed mixture of a substance, okay, that melt or crystallize at temperature that is lower than the melting or crystallization point of individual component. Okay, and eutectic point is it's an invariant point in a phase diagram. So when we say it's invariant point, we mean, remember, the degree of freedom. The degree of freedom is what controls the movement of the system. So when we say the degree of freedom is invariant, we mean the degree of freedom is equals to 0, and then it means now the temperature and pressure, they will remain constant at that point until one of the components are consumed. Okay, or one of the component or the phase is consumed, right? Because when it comes to phase diagrams, we know that the more the components or the phases are being added into the system, okay, the more we are making now the system to not move, okay, or the degree of freedom to be 0, okay, because we're increasing the number of the components. Okay, so this discussion about the degree of freedom is also discussed in that video. The solid solution systems, okay, special plagioclase phase diagrams. All right, so when the temperature at that point, eutectic point, the temperature is constant, and then the system, it won't move. It means now for the system to move, one of the component, it must get to be consumed, and then the temperature will no longer be constant, and then it will decrease a bit, and then the system, it will now become a univariant or divariant. Okay. And then in phase diagram, the eutectic point represents the lowest possible melting temperature of a mixture of two or more components at a specific composition. Okay, so if you were to imagine you having a phase diagram for a binary mixture, which means it involves two components, the eutectic point is the point on this diagram where the solid phases of the two components and the liquid phase are in equilibrium with each other at the lowest temperature possible. Okay, so it means that both the melt and both the melt and the solid, they are in equilibrium at that at the lowest possible temperature. Then the system, it won't move. They will always be in equilibrium until one of the system, it gets to be, of the component gets to be consumed. And then once it's consumed, then the temperature is no longer going to be constant, but it will go a bit down. Okay, or it will decrease. At the eutectic point, if you cool the mixture down to that temperature, it will solidify directly into two distinct solid phases instead of staying as a mixture of solid and liquid. Okay, and then this phenomenon is what you call the eutectic solidification. So eutectic points are crucial in material science and metallurgy because they define the conditions under which certain alloys solidify into specific microstructures, which can affect the material's properties like strength, hardness, and the conductivity. On the other hand, we've got what you call the peritectic. Peritectic is when there is a reaction between a solid and the liquid to form a new different solid, in simple terms. Okay, it's a reaction between solid and the liquid to form a new different solid. Okay, so the point on a phase diagram where a reaction takes place between a previously crystallized phase and a liquid phase and produce a new solid phase. When this point is reached, the temperature must remain constant until the reaction has come to an end, that is to say, until the melt is completely consumed. And then a peritectic point on a phase diagram is also an invariant point. It means the degree of freedom is 0, which is why the system, when the system is at this point, it won't move because the temperature, they are constant. But after you consume one of the, especially the liquid, then it's then that now the temperature can go down and the system can now move. Okay, so in phase diagrams, the peritectic point represents specific temperatures and composition at which one solid phase transforms to another solid, okay, in the presence of a liquid phase. I hope I've explained that previously. Imagine you have a phase diagram for a binary system, okay? The peritectic point is the point on this diagram where the solid phase of one component reacts with the liquid phase to form a different solid phase on the same component. This reaction occurs at a specific temperature and composition. At the peritectic point, if you heat the mixture to that temperature, and the solid phase will transform into a different solid phase, while the liquid phase will also be, while a liquid phase will also be present. This transformation involves the dissolution of the original solid phase into the liquid phase, followed by the precipitation of a new solid phase. Peritectic points are important in material science and metallurgy because they define conditions under which certain alloys undergo phase transformation, which can influence the material's properties such as hardness, strength, and microstructure as well. So eutectic and peritectic points are both important concepts in metallurgy and material science, particularly in understanding phase diagrams and the behavior of alloys during solidification and melting. The key difference between eutectic and peritectics lies in the type of reaction that occurs during cooling and heating, and I've already mentioned those. So what happens about the eutectic during crystallization and also during what you call melting? So during crystallization, at the eutectic point on a phase diagram, a eutectic reaction occurs, okay, during cooling. Then this reaction involves the simultaneous solidification of two or more different phases from a liquid solution. Okay, then it means we have a liquid now. Let's say we're having a solid and the liquid, and then when we reach that eutectic point, another new crystal enter into the crystallizing phases, or it joins the party. So now it means we're gonna have two or more solid phases that are now crystallizing simultaneously or at the same time, okay, from that liquid. But I'm going to show you what do we mean. Okay, specifically, it represents the lowest melting temperature of any mixture of components in the system, resulting in the formation of a eutectic microstructure composed of distinct phases. But during melting, during heating, the eutectic alloy will remain solid. Okay, you'll see when I'm showing the diagrams, it will remain solid until it reaches the eutectic temperature, at which it will now melt directly into a liquid phase without further change in temperature until all the eutectic composition is melted. It means if, for example, you were to crystallize, let's say the first crystal to form is A, and then we still have plus melt. All right, and then when we reach a eutectic point, this melt will crystallize new thing. Let's say now it's B. All right, so we crystallize B. It means now still at that point both A and B keeps on forming. They keeps on forming at the expense of this melt. Okay, they keep on forming at the expense of this melt. So it means now during this is when we go this way is crystallization. When we go this way, it's melting. So when it comes to melting, so when we reach that point, this all B must keep on melting until all of B is melted, and then we now remain with A plus melt, which is why we're saying the eutectic alloy will remain solid until it reaches the eutectic temperature, at which point it will melt directly into a liquid phase without further change in temperature. So it will wait there, okay? Because when we reach that temperature, it is constant, okay, without further change in temperature until all of the eutectic composition is melted, and then we're gonna have A plus. We're gonna have A plus B. I hope it makes sense. Okay. So, what about peritectic? When it comes to peritectic, when it comes to peritectic during crystallization, at the peritectic point on a phase diagram, a peritectic reaction occurs during cooling. Okay, this reaction involves the solidification of one phase and the simultaneous formation of a different phase from a liquid and a solid phase. It typically represents the temperature at which one solid phase transforms into another a solid. So, but during melting, okay, a peritectic alloy will remain solid until it reaches the peritectic temperature. At this temperature, the peritectic reaction will occur, resulting in the transformation of one solid phase into another solid phase and a liquid phase. Okay, so so I hope you understand now that I remember I told you that I told you that during melting, sorry, let's start with saying, remember, at the peritectic point, the solid plus melt, they react to form a new solid phase, okay, with that is totally different from the first crystallized phase. Now, when you melt, it will also mean you have to consume that, or you have to melt that a newly formed one until you remain only with that melt or the previously precipitated crystal plus that melt. But I'm gonna show you what do we mean, okay? So the other thing that we understand before we deal with the example is equilibrium crystallization and fractional. Okay, so equilibrium crystallization, in simple terms, it means when you cool the temperature, you're gonna crystallize the new minerals. But now those minerals, they are in equilibrium with what we call the melt. That is to say, after forming that crystal, you don't there's no separation. They coexist together. Okay, they coexist together. But when you're talking about fractional crystallization, after forming a crystal, then there's what you call a separation. So it means because of the difference in densities, right? The newly formed crystals, they will settle at the bottom of that chamber, and then making now the magma or the magmatic composition to evolve. Okay, to making the magmatic composition to evolve. So fractional, it means crystals are not in chemical equilibrium with the melt as they form. That is, they are immediately removed from being in contact with the melt. Okay, then settling at the bottom if they are more dense, but they can float if they are less dense than the magma itself. Okay, so I hope sorry about that. I hope it makes sense. So what about the melting? During melting, it means this would occur when solid and liquid phases are kept together as the melting progresses. Now it means then for a fractional, then the two after melting, they still get to separate. They are not kept together. So this occurs if the liquid is removed from the solid as the melting progresses. As the melting progresses, then the liquid it gets to be removed. So they all have the same analogy. That is to say, melting and crystallization in terms of being in equilibrium or being in fractional crystallization. Okay. So over here, let's consider sorry about that. Let's consider this composition X. Let's consider this composition X, and then with this composition X here, we are having, let's start with the system. We are having the system between forsterite and enstatite, and also between enstatite and quartz, and also generally forsterite and quartz, right? Yeah, so we want to apply what you call equilibrium and fractional crystallization, and we want to apply what we call the eutectic, and we want to see these eutectics and peritectic points. We want to see all those, and then try to understand now also the crystallization history and the melting history of the composition X, Y, and Z. Okay, so let's start with what we call the composition X over here. What's happening? Okay, so we start with this bulk composition at this temperature. This is our bulk composition. Then now we want to know what will be the end product of crystallization history of composition X. Remember, composition X, it goes all the way until it reaches this point. All right, it goes all the way sorry about that, until it reaches this point. But then want to know what will be the end product. Okay, if we started with composition X. I mean, you'd agree with me that because this composition falls between the composition of the forsterite, the pure forsterite, and the pure enstatite, it must end its crystallization history containing only the crystals of forsterite and enstatite. That is to say, no quartz will occur in the final crystalline mixture. So this composition X, it will end its crystallization history with the pure forsterite and the pure enstatite. Will the quartz occur in the final crystalline mixture? Explain. As I said, no quartz will occur in the final crystalline mixture. This is because the composition X falls between the pure forsterite and the pure enstatite. I hope it makes sense. So it must mean it must end its crystallization history with the forsterite and enstatite. If a mixture such as composition X is taken to a temperature above its liquidus, we are here. Remember, this is the liquidus line. This line is the liquidus line. This line is the liquidus line. So if the temperature is taken to a temperature above, if a mixture such as composition X is taken to a temperature above its liquidus, okay, that is to say above 1,800. So above anything above. Okay, it might be here, it might be there, whatever. Okay, so what will be the state? I mean, we know according to the definition of what liquidus line is. Liquidus line is the line that above it we find only the melt. So it means the state it will only be in the liquid state. Okay. Now, let us now trace the cooling history of composition X. Explain this path fully from the beginning until the final product. We want to explain this until we only remain with forsterite and enstatite, because we already mentioned the fact that it will end its crystallization history with that forsterite and enstatite. Now, I want to bring this to your attention that now, remember, above the temperature of 1,800 degrees Celsius, we are in the zone of all the melt. But immediately when we hit this line at the temperature of 1,800 degrees Celsius, that's where crystallization happens. So I want you to understand that as the liquid of composition X is cooled, nothing will happen until it reaches the temperature 1,800 degrees Celsius. So at this point, the crystals of the forsterite will now start to precipitate out of the liquid. Okay. the first crystals that will form will be the crystals of the phosphorite. They will be the ones that will start to precipitate out of the liquid. So as now the temperature is further lowered, all right, as the temperature is further lowered, remember, okay, first and foremost, if you want to read the composition of the phosphorite, remember this is the liquidus line, so the solidus line will be somewhere here, okay? So, and then it will read its composition. So it means the first crystal, they will have 100%, they will be of pure phosphorite. Okay, but as we lower temperature, the temperature, the composition of the liquid, it will change along the liquidus line. It will change along the liquidus line. It will change along the liquidus line. It will go down like that. Okay. It will change along the liquidus line towards what? Towards what you call a peritectic point. Towards what you call a peritectic point, where in this, it's the peritectic point. Okay, it will change. So the liquid composition, it will change along the liquidus line towards what you call the peritectic point. And now the crystal forming from the liquid will always be pure phosphorite. Will always be pure phosphorite, because now even if we were somewhere here, the composition will just go here. If we are here, it will just be there. If we are here, it will just be here. Do you see? It will always be a pure phosphorite until we reach this point. And then the liquid composition will be changing along the liquidus line, and then as we approach in this peritectic. Okay. Now, what will happen at this peritectic point? Remember, as per definition, we said this is a point wherein the previously precipitated crystals, they react with the liquid to form a completely different new solid. Okay, so it means now at the peritectic, at the temperature of the peritectic of about this temperature is about 1580 degrees. So this is the temperature of the peritectic here, 1580. At the temperature of 1580 degrees Celsius, there will be now 3 phases that are in equilibrium. Which are those phases? At this point, we have phosphorite, we have the liquid, okay, and then now remember, we're gonna now form a new thing, which is what we call an astatite, because the previously precipitated crystals were the crystals of phosphorite, and then now at this point, with this previously precipitated crystal, they react with the liquid to form a new phase, which is astatite. Remember, which is astatite, because now the crystallization history must end with phosphorite and astatite. That's why we are now having 3 phases at this point. Okay? Okay. So at this point, some of the crystals of the phosphorite, they must react with the liquid to produce the crystal at this point. This is the statement that or the formula or the equation that I've just told you about. Okay, so now as I've showed you the reaction, but now remember we said the peritectic point is an invariant point. It means when we say something is an invariant point, it means that the degree of freedom is equals to 0. But now we know that the degree of freedom is just what is that formula? Why do I forget the formula? I think it's somewhere else. I think it should be C minus P plus minus 2. Okay, let's experiment that. Then how many components do we have? We have got phosphorite and astatite. We have got 2. How many phases? We have got 3 plus these 2. All right, and then 2, and then minus 2 plus 2 minus 3 plus 2, it will be what am I saying? What am I saying? I'm saying, am I calculating okay? Am I calculating okay? Because now we'll remain with minus 1. Okay. Oh, I think it should be like this. Then negative times negative, it will be positive. Then we are not doing it correct. No. The components. Oh, the components must be 3. I'm sorry about that. Yeah, I'm sorry about that. Now, okay, C minus P plus 2, because the components we have these components of this diagram is phosphorite, enstatite, and quartz. I'm sorry, it's 3 minus how many phases do we have over here? We've got phosphorite, liquid, and enstatite. We've got 3, and then we've got plus 2. Okay, and then 3 minus 3. Okay, 3 minus 3. All right. So yeah, I'm sorry about that. I mean, the variable that it's affecting our system in this case, it's temperature. All right, and the number of components, it's the phosphorite and the quartz. Okay, so it means the components it's phosphorite plus quartz, which is just equal to, and then it means we only have 1. And then what about the faces here at the peritectic point? We have got the phosphorite plus liquid to give us the enstatite, all right. So let's define the degree of freedom is C minus P plus, it must be 1, because now we only have the temperature here. Okay, we only have a temperature. So now let's say 2 components that we have minus 3 faces at that point plus 1. Then it will just 2 minus this is just minus 1 plus 1, which is just 0. Yes, so I wanted to show you that indeed peritectic point, it's an invariant point. So it means this system, it will stay here because now the temperature is constant. Can you now see the temperature is constant? It's constant. So it means the system, when it's here, it won't move because the degree of freedom is equals to 0. Then what must happen is all of this liquid must be consumed to produce more of the enstatite. When we're consuming all of the liquid, when we keep consuming all of the liquid to produce more of the enstatite until all of this liquid is consumed, then we're gonna only remain with the phosphorite and enstatite. All right, then the system, it will now move, and then it goes somewhere here. Then when we are here, if we want to know the proportion of gray will be somewhere here. Okay, so if we want to know the proportion, it means we must use what you call the lever rule, because now after all of this liquid which has been consumed by this reaction, okay, all of the liquid has been what you call out of the reaction has been consumed by this reaction. So we only have the crystals of phosphorite and enstatite which remains. Okay. Now the proportions of the phosphorite and enstatite at this point, okay, in the final crystalline product can be found by applying what you call the lever rule. If you also don't know what a lever rule is, please visit that video in MJ School of Mining and Geology. So we know, for example, if we want the percentage of the phosphorite, okay, if we want the percentage of the phosphorite crystals, it will just be because phosphorite is towards this direction, is towards this direction, and then instantide is towards this direction. So if you want the 1 year the first right, if you want the 1 year the first right, it means we must go the opposite direction. The opposite direction is what you call D. So it will be D plus C plus D and multiplied by 100%. But if you want the percentage of the instantide crystals, the instantide is towards this line, then the opposite, it will be this one. So that means it will mean C plus D multiplied by 100. So that's what we call a level rule at this point. Okay. So I hope it makes sense. Okay. So we now consider the composition Y, and then we assume we are in perfect equilibrium. Okay. Now we ask ourselves, what is the equivalent composition Y? Remember, composition Y is now here. What is the equivalent of composition Y? Okay, so composition Y, if we go all the way, let's go down, 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 let's go down straight. It merges, or it's parallel to the line of the instantide. So the equivalent of composition Y is just what you call it, the pure instantide. All right. Now, what will appear in the final crystalline product if the perfect equilibrium is maintained? Now, only instantide will appear because we are in that line. We are not between something. We are just right on top of that line. So only instantide may appear in the final crystalline product if the perfect equilibrium is maintained. So we're gonna have, we're gonna have only the instantide. Now, if the composition Y is cooled from an all liquid state, at first it begins to crystallize at about 1650 degrees Celsius. So we are here. So we crystallization, it happens at this temperature. Trace the crystallization history. I mean, then you'd agree with me that if this composition Y is cooled from an all liquid state, it first begins to crystallize at this temperature of 1650 degrees Celsius. Now, then obviously it will have at this temperature, the crystals of phosphorite will begin to precipitate from that liquid. It means we start to form the crystals of the phosphorite, or the crystals of the phosphorite will start to form from that liquid. All right, and then what will happen? This will now continue further downward as we lower the temperature. It will continue further downward until the temperature of the peritectic point is reached. So it will continue downward until the temperature of the peritectic is reached. Okay, until the temperature of the peritectic is reached. So in this interval, the composition of the liquid must become more enriched in SiO2. Okay. It must be more enriched in SiO2, and it will fast change along the liquidus until it has the composition of the peritectic. You know, the composition, the liquid composition runs along the liquidus line until we reach what we call the peritectic. I hope it makes sense. So the composition will change along there, the liquidus line until we reach the peritectic. So now at the peritectic point, okay, approximately, I think it's still 1580. All of the remaining liquid will now, remember we've got the phosphorite, all of the remaining liquid will react with all of the previously precipitated phosphorite to produce the crystal of the instantide. Now the temperature will remain constant until this reaction has gone to completion. Then now, after which the only phase present will only be a pure instantide. Okay, because we had only phosphorite, we had only phosphorite plus, remember we're producing the phosphorite. So, and then we had liquid, and then we produced the astatide. All right, and then what happened is, now at this peritectic point, when we reach that point, we've got 3 phases, and we know the degree of freedom is 0. Okay, because now it means for the system to move, remember the temperature is constant. You can see it's constant. It's constant. Temperature is constant. So the temperature will remain constant until one of the phases it runs to completion. All right. Okay, so now how do we come about with only what we call the astatide? Remember, at this point, one of the phases has to be consumed. And then now what happens is, sorry about that. Remember, we've got this phosphoride, and the liquid. So this liquid, it must react with all of the previously precipitated phosphoride to produce what we call the astatide. So this liquid, it will keep on reacting with this to produce phosphoride. Then at this temperature, okay, at this constant temperature, or at this peritectic point, the temperature will remain constant until this reaction has gone to completion. Okay, so it means now we are consuming what we call the phosphoride. We are consuming what we call the phosphoride until now we only remain with what you call the pure. We remain with what you call the pure astatide, which is why we're saying what will be the final crystalline product will just be astatide, because we are just right on top of this line. Okay, I hope it makes sense. Now, if we were to, sorry about that. Yes, so now let's consider this composition Z here. We consider this composition Z here, which now, do you see, where's my, okay, it's here. So if we check, it's between astatide and quartz. So it will end its crystallization history with astatide and quartz. What will be the end product? I mean, you already know the end product, what it will be, just astatide and quartz. Okay. Now, if such composition were to be cooled from some high temperature where it is in there, all liquid state, it will remain all liquid until it reaches the liquid temperature at about 1600 degrees Celsius. Trace the crystallization history. So it means if such composition Z were to be cooled to this temperature of 1600, where is that cooling? Somewhere here. Yes. So if it were to cool down to that temperature, at this temperature, crystals of phosphoride will now start to enter, or will start to crystallize or to precipitate. Okay, and then now we know that the composition of the liquid will always now start to change. But now changing along what you call the liquidus line towards what you call the peritectic temperature, or the peritectic point. Is immediately when we start crystallizing, the phosphoride, then the liquid composition start to change along the liquidus line towards this peritectic point. I hope it makes sense what we are trying to say. So at this peritectic point, all of the phosphoride which previously precipitated, it will now react with the liquid to produce the astatide. That's so far you understand what we're trying to say. Okay. Now, after this reaction has run to completion, all of the previously precipitated phosphoride is consumed. Okay, all of the previously precipitated phosphoride is consumed the same way it has been consumed here. With composition Y. So all of the previously precipitated phosphoride, it will be consumed. Then there would remain, there would still remain what you call the liquid, because remember, the reaction is the phosphoride plus liquid is equals to astatide. So we've consumed this, but we're still having what you call the liquid, isn't it? So with decreasing temperature now, if we decrease the temperature now, what will happen? Remember, we're still having the liquid. So we want to know what will happen if we decrease the temperature. So with a decreasing temperature, more crystals of astatide would form, because now we are using this liquid to form more of the astatide. So and then the liquid composition would change along the liquidus line now towards what we call, remember, we're still having the liquid, isn't it? Now it will now change along what you call the eutectic point. Remember, I told you about what you call the eutectic point, and we said the eutectic point, it's wherein now we have a reaction between two things to form something as well. Okay, so this liquid will change towards eutectic. So at the eutectic point, now the crystals. Remember, we were only having we only let me go there. Remember, when we were here, right? We stopped here because the degree of freedom it was 0. Then the system was saying to us, no, I can't move, guys. Why? Because of I don't have any freedom. And then we asked it, then what must we do? And then it says, no man, because we've got 3 components, make sure we consume 1. So what did we take? We took what we call phosphorite. Then we remain with what we call liquid. So it means now all along now astatite, it reacts with that remaining liquid. All right, it reacts with, so the liquid was forming more of the astatite, while the liquid composition changed. Remember, we're taking the components within that melt which forms the astatite to form more of the astatite. Now the liquid composition, it will change towards the eutectic point, towards this point. It will change towards this point. But immediately when we reach here, then now remember we're between astatite and quartz. Then we're gonna form a new thing, which is what we call a quartz. I hope it makes sense, because the quartz start to form at the eutectic point. So, but now the temperature will also remain constant until the liquid now is consumed, because we said the eutectic point is also invariant. We said it's also invariant when the degree of freedom is just the 0. And we've got 3 things here now. And remember, we want to only remain with astatite and quartz. So it means we must consume now all of this liquid. All right, the system, remember the temperature here is constant. You can see the temperature must remain constant until all of the liquid is consumed. Then now, if we're remaining with astatite and liquid and quartz, then the system, it will now go a bit downward. Then no longer at this constant temperature, it goes a bit downward, and then which is why we are remaining with only quartz and astatite. So I hope you've noted that the composition Z, since it lies between astatite and quartz, it will end its crystallization history with quartz and astatite. So I hope you understand the eutectics and peritectic points. But above all along, we've been talking about a crystallization, but in what you call we were talking about what you call the perfect crystallization. Okay, we were talking about perfect equilibrium crystallization. Okay, so now, sorry about that. So fractional crystallization and melting. Okay, remember with fractional, after forming some things, you have, if you are crystallizing, if you're precipitating some, or you're crystallizing some crystals, you must now separate them from the melt. But if you now have the crystal, and you melt it, that new melt must be separated from the crystals. Please understand the difference between fractional crystallization, melting, and fractional melting. Okay, so under fractional crystallization conditions, the cooling and crystallization histories are different from equilibrium ones. Consider the composition X and thoroughly describe in detail the perfect fractional crystallization history of composition X. Now, the second question is about melting is the opposite of crystallization. If you believe the aforementioned statement, explain the melting of composition X. We're just gonna use only this example of the composition X. We're just going to use only this example of composition X, just to make you aware, or to see what is happening during now fractional, because all along we've been talking about the crystallization the fractional crystallization. I mean, as we were still at the what do you call this, equilibrium crystallization, even if we were to talk about melting, I mean, guys, even if we were to talk about melting, let's consider composition. Okay, let's just talk about this composition Z. Remember, we ended with quartz and enstatite. It means when we start to heat these materials, then we're gonna go straight towards the eutectic temperature. So here the temperature, it will remain constant, and then with time it would now start to increase until remember, quartz, according to a Bowen's reaction series, oh, my quartz, it's orthoclase, muscovite, and quartz, so it's low temperature. So it means when we start to melt, we'll have to start with quartz. Okay. Okay, so but now what happens is quartz will be the first one that now, remember, we're only having quartz and enstatite. We're only having quartz plus enstatite. Now because we are increasing the temperatures, quartz cannot survive increase in temperature. Then now we'll wait here at the eutectic point, and when the temperature keeps on increasing, quartz says, yo, guys, now I can't do this anymore. Then when it can't do this anymore, it will what? It will melt. Then now it forms what you call it forms what you call the liquid. It forms what you call the liquid. So, and then now here we won't move because we've got three now things. We won't move. All right, we won't move. Then what must we do? The temperature must keep on increasing until until what do we call, until one of the phases consumed. In this case is quartz. Then the quartz, it will be consumed, and then we remain with only enstatite plus liquid. All right, and then until all the way when we are here, then we know we're gonna produce okay, then we remain with only enstatite and liquid, isn't it? Then we're gonna go back, and then when we are somewhere here, that's where now also we start to crystallize, to melt the enstatite, and so on until we melt the phosphorite, and so on. Remember, the solid composition will be changing along the solidus line until we only remain with the liquid over here. Then remember that what we are trying to say is we're going to melt a quartz first, then we go up here, we melt enstatite, and then we go up there, and then we keep melting the phosphorite, When we are somewhere here, then wait, so remember which composition we were considering getting? Oh, we're considering composition Z, sorry. So we're gonna melt quartz first, and then we've got when we somewhere here, we're gonna make sure that now we melt the enstatite. So as we're melting, the composition will be changing, the liquid composition will be changing towards the liquid until when we are here. Then when we are here, all of the enstatite will have melted. Yeah, sorry, I forgot what composition we're looking at. Now, can you see that melting is just the opposite of what was just happening? So let's now consider the composition X and thoroughly describe the perfect fractional crystallization. Now we want to know the fractional crystallization. So melting of composition X, okay, is exactly the reverse of crystallization that we have just mentioned. Okay, so mixture X will begin to melt at the peritectic. Remember, we're having phosphorite and enstatite. So the mixture X will begin to melt at the peritectic temperature. So here, when we increase, remember the temperature, let's say we started somewhere here. Then the temperature must rise. When we are somewhere here at this temperature of the peritectic, all right? Then now the melting will start. Okay, because now we were all along we're having the phosphorite plus enstatite. all right? And then they were stable because they are in their field, they were stable. But now, when you increase the temperature, you make them to become unstable. So when they start to they started as being strong, but when they're somewhere here, they be like one of them must start give up. To give up, all right, and then now melting will start here at the peritectic temperature. So at this point, at the ansatite will start to melt. Okay, to what then now to what to the crystals of what you call will start to melt to the crystals of what you call the phosphorite, because remember we're having phosphorite and astatite. So the astatite will melt now. Okay, at this point, the astatite will just melt to crystals of phosphorite plus the liquid. Remember, we were having this and then we started to melt this astatite. So now it means this astatite, it will just melt. Okay, then we're gonna have this plus liquid. Okay. Okay. So I'm explaining what we call melting. I'm explaining what we call melting, but let me start with because my mind is here at the melting of composition. So sorry about that. Let's start with the crystallization first, okay? Because it wouldn't make sense to do the reverse process without starting out to understand firstly the first one, okay? So at the back of my mind, I was thinking we're answering the first or the second question. Sorry about that. So let's do what you call the perfect fractional crystallization of composition X. So we know during a perfect fractional crystallization of composition X, all of the phosphorite, okay, is precipitated, and then somewhere will start to be precipitated somewhere around 1800 degrees Celsius. And when we reach that point, immediately when we crystallize the crystals of phosphorite, then they get to be removed out of the system. That is what fractional crystallization is. When forming something, they must be removed out of the system. Okay. So, but we know that in nature, this occurs by crystal sinking to the bottom of the liquid due to the fact that crystal generally tends to be more denser than the liquid. So then you agree with me that the crystals, after being formed, they get to be removed from the liquid and then they sink. Okay. Okay. So I hope you understand. So let's now start the cooling history. So that liquid, okay, when it cools to that 1800 degrees Celsius, it will cause now the phosphorite to come to now crystallize. Okay, now then with further cooling, the liquid composition then will always change along the liquidous line. And then now more phosphorite, it will be now precipitated as we are moving, as the liquid composition changes along the liquidous line. Then more of the phosphorite, it will keep on being produced and at the same time moving, because remember, for the liquid composition to move, to change along the liquidous line, is because we are forming more of the phosphorite and removing them. Okay, for example, I always give people this analogy that with fractional crystallization, let's say we've got these three let's assume they are circles, and these nyana things, they are 3 all right. So we've got equal proportion, but when I form the phosphorite and I remove them, it's like the liquid, it's changing or it's increasing. Oh, sorry, but this cycle is like they're increasing. Then I remove the other one, so it's what you call the increase relative to one another. All right. So now can now see that now these ones, it's like they're increasing, but in real sense they're not increasing. It's just that you are removing other things. So which is why during fractional crystallization, when you form this phosphorite and then you remove them out, you remove it out of the system, then the liquid composition runs towards the or runs along the liquidous line. I hope this story makes sense, because with fractional, you remove what you have just formed. Okay, so since as this liquid composition changes along the liquidus, Okay, so more of this phosphorite will just keep on being formed, keep on being formed until, where is that? Yes, it will just be kept on formed as this thing it's running along that line. So in this case now, all of the phosphorite, it will be removed from the system as it crystallizes. All right. Now, since the phosphorite is no longer present in that system, okay, the composition of the system will have the composition of the of the liquid. Okay, because now the phosphorite is no longer in the again, it was formed and then kept on being removed as the liquid change along the liquidus line. So it now in that melt will not have any components that can form that phosphorite. I don't know if it makes sense. So then all of the phosphorite now it's completely removed out of the system. Okay, so because it's no longer present, now the composition of the system will have the composition of the liquid. Okay, now what do we mean by that? We mean that the temperature, it will now at that point reaching what you call the peritectic point, because all along it was moving along as we were keeping on forming the phosphorite and removing it out of the system. The liquid, it was changing towards what you call the peritectic. So once we are here, then all of the phosphorite, it's no longer present in that system. Okay, then the composition of the system will have the composition of the liquid. I don't know if it makes sense, because the phosphorite removed can no longer contribute to the composition of the system. The phosphorite composition can no longer contribute to the composition of the system. Of course, for obvious reasons, it has been removed. Okay. So therefore, when the temperature reaches this peritectic, when the temperature reaches this peritectic temperature of 1580 degrees Celsius, there will be no phosphorite available to react with the liquid. All right. Remember, we know the peritectic is when the previously precipitated react with the liquid to produce new things. In this case, astatite. But now, we make sure that by the time we reach this peritectic, we don't have any phosphorite. So the phosphorite can no longer contribute to the composition of the system. All right, they will no longer take part in or it does no longer participate in chemical reaction. So we don't expect at this peritectic point, we don't expect the reaction between phosphorite and liquid to produce what? To produce now the astatite. Okay, all right. Now what will happen is these systems are clever. Okay, the liquid in itself will start in its own, because remember, it does not have in that system, we don't have any phosphorite anymore. Then the system would be like, okay, do we mean because we don't have phosphorite our lives should stop? Then the system says, no, man, no, I've got something in my storage. I still have what? I still have liquid. Remember, this one is no longer there, but I have this one. Then how can I use this to my advantage? Then the liquid will now precipitate the crystals of the astatite and continue to cool towards the eutectic, where the crystals of the quartz will now start to form. Okay, then now, which is why the final crystalline product, it will consist of only the now the astatite and what we call the quartz. Okay, when we're talking about this composition X. Okay, because now remember here we start to produce the liquid started to produce what you call the astatite. As the temperature goes down, the liquid start to produce the astatite, and then now we've got the astatite plus the liquid. But now as we go down, the astatite gets to be it gets to be formed and then be removed out of the system. Get to be removed out of the system. Then now, what do we make? We make now, or we force this liquid to change towards what you call the eutectic point. To change towards what you call the eutectic point. But now, when we get here, the system we know that now we must now start to form the quartz. But then man, then we'd be like, no, man, no. Because we've been precipitated the crystals of astatite, and then this the cooling happens towards the eutectic, then where we start to form the quartz. Now, when we are somewhere here, because remember the final product is quartz and astatite, then it means when we reach this point, the crystals of the astatite, they react with that liquid to produce what do you call it the quartz. And then the system, it won't move when we are here because we've got three phases, and then we must remove all of these liquid to only remain with the quartz and astatite. Now it means we'll end our crystallizing history with what you call the quartz and astatite. Okay. Now, can you note that under the equilibrium conditions, the final crystalline product of composition X consists of the phosphorite and astatite. But wow, while now in under fractional crystallization, we now have only the quartz and astatite. Confusing? No, it's not confusing. It means a fractional crystallization has allowed an originally phosphorite-rich composition to produce a silica-rich liquid. And then that's where the quartz appears in the final product. And this has the analogy with the fractional crystallization that it's happening in the igneous system. For example, wherein we're having the magma that ranges from felsic all the way to ultramafic. So when we during fractional crystallization, the first thing, okay, it's fine. So it's fine. Let me not use that one. Let me use the Bowen direction series. I hope it will make a perfect sense. We've got old people are boring, and then we've got all my quartz. We've got all my quartz, we've got calcium here, we've got whatever here, sodium here, and olivine, pyroxenes, amphibole, biotite, orthoclase, muscovite, and quartz. Now, during fractional crystallization, or during crystallization, we know crystallization, we start to crystallize high temperature materials. In this case, we're talking olivines and pyroxenes. So we form these ones and then we remove them out of the system. What do we force? We force the composition of the liquid now to change towards the felsic side. Remember, from the top, it's mafic. And then at the bottom, it's at the center, it's intermediate. Then at the bottom is felsic. So because we've removed the mafic components out of the system, we now make the melt to only remain with the intermediate melt and the mafic melt. Now that intermediate melt, it will now crystallize the intermediate materials, things along here. Okay. Then now, because now it's fractional, after forming, you remove them, you take them out. Then let's take them out. Let's take them out. They are no longer there. Then it means now the liquid composition is now felsic in composition. We only remain with my quartz and my muscovite. Oh, that's why at the end we'll now crystallize the silica rich. So, which is why we are saying thus the fractional crystallization it allowed an originally phosphorite-rich composition to produce an SiO2-rich fluid, which is why now quartz appears in the final crystalline product because of the fractional crystallization. This is far different from the equilibrium crystallization. I hope it makes sense. Guys. So if you're still struggling to understand these concepts, please, you are more than welcome to drop a comment in the comment section, and we will try to Explain again. Now, let's answer this. Let's answer the second question. Now, if you believe that the melting is the opposite of crystallization, then now explain the melting of composition X. All right. Now remember, the mixture X will begin to melt at the what you call the peritectic temperature. Okay, will begin to melt to melt at the peritectic temperature at the yes at the peritectic. Okay, so at this point an astatite melt. Okay, at this point an astatite melt, because as you increase the temperature, the astatite melt will. All right, no, remember we are here. We are not here. We ended our crystallization history here. Okay, so we are no longer here because we are no longer discussing the melting under the perfect equilibrium. Okay, we are no longer discussing that. So now what do? It will start to melt the quartz first, because during melting we start with when we're looking at the boundary reaction series, then we start to melt the low temperature first. So we're going to melt this one and produce the melt over here, and then until we now start to see the peritectic, we start to see the phosphorite that enter into the crystallizing phases, and then remember we produce. Remember, it's just the reverse. We had the quartz and astatite. Then now what's happening? Remember, we have the quartz and astatite. Now what's happening? It's this quartz must now melt, because it's when you increase the temperature, it will start to melt. But melting start to happen here. At this, when we are looking at the composition X, the melting, it will start here. It will start here. Then when the melting start here, quartz, because it's a low temperature mineral, it will not withstand high temperatures, then it will start to melt. But now, because it's fractional, these quartz must melt. But as melting happens, after forming that composition of the felsic, okay, of SiO2, we remove it. Melting will remove it. Melting, it will remove it until all of the quartz has melted. Then once all of the quartz has melted, now we remain with what we call the astatite. Then now the astatite must start to melt. Then now start to melt until we are in this region where in now the remember we were melting astatite, and then but remember we are consuming that astatite. Okay. So, so when all of this astatite crystal has been consumed, then the temperature can now increases until somewhere around 1,800 now until here. Okay, so it was here, yes, and then it will now, in the temperature, it will now increase until somewhere here, 1,800 degrees Celsius. So, and then at which point all of the phosphorite crystal would have now been consumed, and the only phase left, it will now be what you call the liquid composition. All right, we started to melt with the quartz, and then we produce the liquid, and then that liquid, we kept removing it now until all of the quartz has been melted, and then now that astatite now must start to melt, and then the astatite must start to melt. Remember, here we are having we are somewhere here. The phosphorite, remember, it's there now. The phosphorite is there now. So we're having the astatite plus phosphorite. Remember, again, the liquid, we keep removing it. Right? Remember, I don't want to confuse you. The first thing, we melted the quartz. and then produced the melt, then that melt we kept removing it. Then and then we are remaining with enstatite. Then enstatite we melt it, and then we melt it, and then when we melt it, we remove the composition of the enstatite. We remove the composition of the enstatite. As this thing now moves towards the peritectic point, when we are here, then we have now the phosphorite. The phosphorite start to melt here. Then when we melt that phosphorite, the temperature keep on increasing until we reach 1,800 degrees Celsius. Now, until now, all of the once we are here, all of the phosphorite it will be consumed, completely melted, and then will remain with only the liquid. I hope it makes sense. I hope it makes sense. Sometimes I feel like maybe I'm being fast, but I hope all of these things they make sense. So in today's lesson, we've learned about equilibrium and fractional crystallization, and equilibrium and fractional melting. Okay, we have observed the melting under both equilibrium and fractional, and the crystallization under both equilibrium and fractional. And we've also learned about the points, peritectic points and the eutectic points. Okay, and I hope you understand these things. And we've also learned what's happening if we having the bulk composition that is starting between two end members. It means the crystallization history it must end with these the end members that the bulk we started with. So basically that is that about the eutectic and peritectic systems. So guys, your support is it means a whole lot to us. We are really thankful. Please don't like to subscribe. Don't forget to subscribe, like, share, comment, and if you have a topic you want us to cover, you are more than welcome to comment in the comment section, and we will be pleased to do that. And still, if you don't understand, if you have some queries, you are more than welcome to drop your comments in the comment section, and we will be happy to assist. We wish you all the best in these processes, especially the people in the metallurgy, okay, because the phase diagrams they use these things, okay. But to the geologists, especially the igneous petrologists, they use these phase diagrams to understand the crystallization history and the melting history. So until next time, cheers.